delighted to introduce you all Mr. Sanjeev Srivastava. Sanjeev Srivastava is a senior digital transformation leader with over 30 years of experience in digital transformation, global customer success delivery, engineering and design and development. Sanjeev Srivastava is founder, director of Joix Technologies Private Limited based out of Hyderabad. He received his MS in Microelectronics Technology and Manufacturing Management from École Nationale Supérieure de Mines Saint-Étienne, France. He is an alumni of College of Engineering, Osmania University, and completed his undergraduate in Electronics and Instrumentation in 1994. He completed his MBA in Operations Management from IGNOU, Delhi. He worked in R&D departments of various leading electronic design companies before joining Synopsys in 2000. At Synopsys, he started his career in Design Services Department before moving to the Global Technical Services Organization in 2002. He has built and led a strong team of applications engineers for delivering technology services for their global and Indian clients. Sanjeev has a proven record of building high-performance team, maintaining strong technical and working relationships with customers, field teams, and international support organizations in India, South Korea, Japan, Taiwan, South Europe, and Vietnam. Sanjeev is working as adjunct professor in OU College of Engineering, Hyderabad, and is also actively taking place in Board of Studies of ECE in Department of Electronics and Communication Engineering. We gladly welcome you, sir.
Thank you.
To deliver you.
Thank you. So I'll give a brief introduction about how is the Indian semiconductor industry landscape looking like and what's driving the innovation, why this thing has become more important. Then a little bit of basics of MOSFETs. I'm not going to go deep into it. I know some people can just sleep, but I'm going to have it at a very high level. And then introduction to the compound semiconductor, that is silicon carbide and gallium nitride, and why it has certain advantages that silicon does not provide and its application areas. Okay, so let's get started. So as you can see, the Indian semiconductor demand is increasing year after year to an extent that it is growing at a compounded annual growth rate of 26.3%. So that's a massive growth that we are seeing in the entire Indian semiconductor market, and I'm sure like that 95% of this demand is met through imports, which means there's a lot of foreign exchange dollars that is going out in terms of imports, and it also happens to be second largest importer of semiconductor. So in terms of countries from where we are importing this thing, countries like China, Taiwan, Hong Kong, Korea, Japan, these are countries from where we are importing bulk of the semiconductor, and it has become very, very strategic for the Indian economy that we have self-sufficiency in terms of manufacturing our own semiconductors. But the big problem, and we know that we already have a fab in the Chandigarh, but that's a very small fab. It's not a commercial fab. And what we need to do is, how do we get there? Because there are numerous application areas where we need this semiconductor, and that was, how this whole semiconductor mission came into picture. And the things that are driving it is the low cost labor cost, because these semiconductor fabs, manufacturing fabs are labor intensive, and it needs a huge ecosystem when you are having this thing. My master's was in France, as she was telling, and I had an opportunity of working in a fab that was ST micro fab. And so typically when there is a fab, there is an entire city built around that thing. There's a huge ecosystem. So it's no more just one standalone fab. There is a huge ecosystem, and I think that is what we are trying to build here in India as well. Coming to the supply chain efficiency, India also has, it's on the crossroads on the trading routes. So that way, a lot of trade goes through India, and that way also, it helps us logistically also to be to start manufacturing, so that we take advantage of our geography in terms of supply chain management and the emerging ecosystem. So in terms of design, we have an excellent ecosystem, and right from 1990s or late 1990s, because when I graduated from here, the VLSI was not heard of a lot. There was no opportunities in VLSI design areas, but after two or 3 years, I started started seeing the job openings coming up in the semiconductor area, typically from ST Micro, TI, analog devices, and so on. So coming down to the fab, we are right now focusing on 3 type of fabs, and as you know, there are 3 fabs that are coming up in Gujarat. Okay, one of them is the actual the front end of manufacturing fab, that is a wafer fab, and the other 2 ones are mostly assembly and testing fabs, and the one that is coming in Assam is also assembly and testing. And why assembly and testing? Because the cost of establishing that fab is much lower than the main fab, the manufacturing fab. So that's the reason they went with that thing. That's a good strategy. Then we have a few fabs that are come in the compound semiconductor area, which is silicon carbide and gallium nitride. So the cost of setting up a fab for a compound semiconductor is 1/10 of a conventional fab. Reason being, based on the wafer size and the clean room that is required for setting it up, those costs and the manufacturing cost, that is the lithography and other equipment cost, is much lower for the compound semiconductors. And then is the display fab. Again, everything, we are importing a lot of, even the companies like Samsung, LG, and all the other companies who are manufacturing their television sets and other things, they are importing the display semiconductor from outside. They are not manufactured here. We are only assembling here. So there is also a proposal to come up with a display fab. So having spoken about this thing, let's see what is driving this demand. So it's not surprising that automotive, data center, renewables, and mobile, they are driving this innovation. And as we know, automotive is now having a big part of the semiconductor getting inside that thing. Same thing with the data centers. Any idea why data centers are seeing a huge demand across India and across the world? Why are we seeing a huge demand in data centers? Yeah, so there are technologies like 5G, there is e-commerce, there is social media, everything is, everything is networked, everything goes to the data centers. And just in India itself, we are having close to 200 data centers, and even outside also. And then you have all the renewable energies. Every country is having their own sustainability goals, and based on that thing, more and more manufacturers are moving their automotive to EV mode, and also the renewable mode, which includes your wind turbines, solar power, and many other renewable energy sources, and the mobile thing. So what is one thing that is worrying the engineers? Okay. So as an engineer, we always think about, okay, about the design and all that thing, but there are other things also that engineers worry about. And typically in your, when you start working in corporate, there are things that engineers, they keep thinking about them at night. So high power density, lower cost, lightweight, better thermal management, and smaller size. And if we take from the previous example, if we take a data center, we obviously need a high power density, and the reason being, like, if you don't have a high power density, then the real estate that you need to have this data center will be much higher. So it is very, very important that you have a high power density, which means for a certain square feet of a space, you should be able to power all the servers in that space. Lower cost, of course, cost is a big constraint, and in technical world we can talk about all the technology and all, but at the last the buck stops at the cost. You know, everything is cost driven. All the decision, even if it is technical, everything is cost driven. Okay. Lighter in weight, again, lighter in weight also impacts the cost, because the rack space that you have there, if they are very, very heavy, then you know you need additional supplements to support that thing, so it has to be lighter in weight. Better thermal management. If you know, most of these data centers are also cooled by air conditioners. Reason being, there is a lot of power dissipation that happens. So the lower is the power dissipation, the lower is the capacity of the AC that has to be installed, and lower is the power consumption by these ACs. So it's very, very important that we have a very high efficiency power converters and the power supplies that power these data centers. And smaller in size. Again, smaller in size is a form factor that we are talking about. We would at best like, you know, these, you know, power devices they have to be very small. I remember from my first company, you know, when I was, I got a job through the campus placement. They were pioneers and in the power conversion industries, and they were supplying it to the telecom industry. So a 10 kilowatt or 10 kVA power converter, DC to DC power converter used to be, you know, almost the size of a refrigerator, okay. And it used to be that big. And then the telecom department told, no, it is not possible. And the challenge that we were facing is the heat dissipation. If there is a lot of heat dissipation, you have to put large heat sinks. And the heat sinks, they take a lot of space, you know, and it becomes very, very heavy also. So we have to move to the power devices which are very, very efficient and also are, you know, they have a good conductor of heat, basically. And then we imported a similar unit from Israel to be tested at the Telecom Authority, and that was size of a small box. So that is the difference that efficiency can make to a power device. So smaller in size is also very, very important. So these all 5 factors are very, very important in the sense that they impact the cost primarily, but they also impact the environment. For example, if you have to, if it is not power efficient, then there is a lot of heat dissipation, and for that heat dissipation, you need to have, you know, a larger ton of AC that are cooling these things. Again, that's a power wastage and also not very good for environment. So let's look into a typical electric vehicle, and here we see that there are different stages of power conversion that happens. For example, from your direct supply line, there is a AC to DC converter, okay, and then that charges your battery bank, which is typically at a 350 volts, and from that the battery bank, there is an inverter, DC to AC inverter. And why do you see 2 stages there? Because many times based on the rating of the induction motor or the traction motor, we have to either boost the DC voltage or we have to reduce the DC voltage. So that is why in the first stage you have DC to DC conversion, and that DC is converted to AC for driving the traction motor. And once this is done, there is also a DC to DC converter for lot of other things that goes into the car. Like for example, your steering wheels, your infotainment system, your power windows. So there is a lot of things that are run on the DC in the car itself. So there is a DC to DC converter required there also. Now the challenge here with the EV electric vehicle is how many kilometers the car can go on a single charge, right? That is what we are looking for. Okay. We have constraint on the weight, because if you increase the battery bank, the weight will increase, and if the weight increases, then you know it needs more torque and there is more current consumption. It is not very viable. So the best thing to do is to reduce the weight of the battery bank. But for that, we have to ensure that whatever battery bank we are having, it uses 100% of the energy for driving the traction motors. There is no you know, wastage that happens, and it has two advantages. The first advantage is that the size of the battery bank becomes smaller, and as a result of having very efficient power converters, there is hardly any heat sink that is required. And these heat sinks are very, very expensive. Not only expensive, they're also very heavy. That also adds to the weight of the car. So it, it works best for them that they have the most efficient power conversion technique while doing this thing, because that is going to, put them in front of the market in terms of having a higher, kilometers on a single charge. So this, I'm talking about to just drive a point that why power conversion becomes very important and what is driving that power conversion, in the behind. So let's look into it. So as you know that power electronics deals with conversion, control and management of the energy, and often it can be from high voltage to low voltage or low voltage to high voltage, DC to AC, AC to DC, and there are so many other things that becomes a part of the power electronics. And this power electronics has also been driven by advances in material science and semiconductor technology. I remember when we started working, and I was part of the R&D team, we used to use MOSFETs, and that was not very, very efficient. And then we moved to something called, for higher wattage DC to DC converters, we moved to something called as IGBTs. Okay, we started using IGBTs. That was supposed to be, better at power conversion, was more efficient, and had better power efficiency also. So if you see here, so basically the efficiency of any power conversion unit is basically the energy that is getting utilized divided by the energy input. Okay. And so whatever loss, the energy loss that we see is basically a difference of your input minus the energy that is utilized. So if we have to minimize this loss, we have to make sure this efficiency is close to 1. Okay. Then we'll have the least amount of loss. So the whole purpose of designing this power conversion using advanced semiconductor devices is to make sure that we have this thing as high as possible. The efficiency is high as possible. So what are the factors that impact the power efficiency? So I already discussed about this thing, but let me again reiterate. So in order to design a highly efficient power power conversion instruments, we need to select a high efficiency power transistors. And this I have mentioned that as we start using much highly efficient power transistors, the losses become less, and when the losses become less, the heat dissipated is also very smaller, requiring a smaller heat sinks, and that reduces the cost of entire unit. Okay. In addition to that thing, we also go for low resistance capacitance, because many of these devices are driven by the current sources, and also we use advanced control algorithms, and as a part of the low power strategy, right, we also do a lot of we try to digitally control the different parts of a system. So the system that is not in use, right, that is kind of put to sleep, so that the power is not going into that part of the design circuit. So that is something that we do in the low power design techniques. And apart from that thing, from the system design perspective, reducing the cable lengths and minimizing switching losses of the devices also helps in improving the efficiency. So to attain all these things, right, because for a long time we were using silicon, but for a high voltage, high temperature applications, the silicon was not very appropriate, or it had its own limitations. So the best way of addressing those limitations was to go for a wide bandgap semiconductors, which are basically the ones that are very popular are silicon carbide and gallium nitride, and these are widely used in the power converters and inverters, and has much better properties because it has higher efficiency, faster switching speeds, can operate at high temperature and voltage. So this, when we use these semiconductors, it helps us to make sure that we have a smaller, powerful and more efficient power conversion devices. So let's now that we have discussed about the various power transistors, let's talk about a little bit about the MOSFET basics. So basically, your MOSFET, it's a switch, which when you apply a gate to source voltage, it conducts, otherwise it is in open. So basically it is a switch, and when the VGS is greater than the threshold voltage, it starts conducting. Okay. So this is basic operation. And so for every MOSFET, right, there are other losses also, but primarily the dominant ones are two losses, that is the conduction losses and the switching losses. So we'll talk a little bit more about the conduction losses and the switching losses in the coming slides. Okay. So the conduction losses is nothing but the I square R losses, right? So you know that whenever there is a flow of current through a resistance component, there is a voltage drop and there is also a power loss that happens, and that power loss is denoted by I square R. Okay. So here you see that this is a pulsed signal that is given to the gate. Okay, and based on that thing, you see that the ID is also pulsating here. So basically, it is not the complete ID on, but based on the duty cycle at which it is getting pulsed, you get a sort of an average of this thing, or what we call as a RMS value of it. So as you can see here, the conduction losses, or the power loss due to conduction is I square D for the on status, and then RDS, that is resistance drain to source, again during the on stage, and multiplied by the duty cycle. Okay. So the ways that we can actually reduce this thing is to make sure that this RDS on, when we are selecting a power device, this RDS on is as small as possible, because you make the RDS on small, the conduction losses also decreases. Now let's talk about the switching losses. So when we talk about the switching losses, like we can talk about the ideal switching device, where when you apply a VGS, we would assume that the VDD, when it is on, it comes to 0 instantaneously, and same thing with the ID also, it rises almost immediately. But in the real, it doesn't happen that way, because there is always a time lag that happens, for VDS to fall or for the current to rise. And because of that thing, there is something called a switching loss that happens. Okay. So here is the formula for the switching loss, that is the energy during the on stage. So that is ID on multiplied by VDD into this is T rise of current and T fall of voltage divided by 2, and multiplying that thing with the switching frequency, you get the power loss during the on stage. A similar thing can be seen during the off stage also, and basically the power loss during the off, when the MOSFET is getting switched off, is your E off multiplied by the switching frequency. So higher is the switching frequency, higher is the loss. Okay. So what you can do in order to reduce this thing is, okay, switching frequency is something that it is better to have a high switching frequency as possible. But what can be done is basically reduce the time to rise and the time to fall of your voltage and current as small as possible. Okay, and that is only possible when you actually engineer your device to have a much smaller electron mobility or hole mobility, or in general sense we call as a carrier mobility. So the higher is the carrier mobility, the faster is the rise time and the fall time. So this is the MOSFET loss by operating voltage. So you can see that the larger part of the losses are contributed by the conduction losses. Okay, and the switching loss is kind of similar, as you increase the voltage here. Okay. And by the way, this is only a percentage, right? This is not absolute number. These are percentage. And same thing for the frequency also. So as you, increase the frequency, you will see that the losses due to reverse recovery or switching off or switching on, that is increasing because of increasing in frequency, whereas the conduction losses remains same. I'm not going to go very deep into it, but one thing interesting that you have to notice here is the temperature dependencies on the leakage current, right? So this is leakage current versus the temperature. So as the temperature is increasing, the leakage current increases exponentially. So that is the reason it is very, very important that we control the temperature, because once the temperature is beyond a certain limit, the leakage current increases, and then there is losses because of the leakage current. So it is very, very important that we keep this thing in control. And the problem with the silicon devices is beyond 125 degrees centigrade, it becomes very difficult for an engineer to control the characteristics of the transistor. And if the temperature, the junction temperature increases, it also changes the electrical parameters of the MOSFETs. So it is very important that we keep the temperature in control while designing the whole system. And same thing is with the RDS on also. So RDS on, basically with increase of temperature, your RDS on is also increasing linearly or more than linearly. And what happens is, if the RDS on increases, your conduction losses also increases. So it is important that we choose a device where there is not much difference or increase of RDS on with increase of temperature. Okay, so let's talk a little bit about the energy band gap. So a typical, so I'm sure like we have all studied this thing in our intermediate or say in the engineering. So basically insulators, they have a huge band gap, energy band gap, which is typically more than 5 electron volts. And because of this huge band gap, at an ambient temperature or even at a higher temperature or with application of voltage, there is hardly any electron that will jump and move to the conduction band. And that is why, the insulators are very good insulators. They don't conduct the electron or holes, and primarily it is because of the large band gap. Coming to the conductors, the valence band and the conduction band almost overlaps. So the entire, all the valence electrons which are there in the outermost orbit, they become part of the conduction band and are available to move freely within that conductor for conducting your electricity. Coming to the semiconductor, this has a smaller band gap compared to the insulators, typically in range of like 1.1 electron volts. And that is where it becomes very interesting, because now it can act as a switch. Now we can switch it off or switch it on based on the electric field that we are giving. Okay. So the popular semiconductors that we use is typically your silicon, germanium, and now we have the new semiconductors, compound semiconductors like gallium nitride and silicon carbide. We'll talk more about that thing. And here you can see the energy band gap for the different materials. So let's go a little bit deep and talk about the silicon carbide and the gallium nitride and why it is important for the future of the power electronics. So let's talk about silicon carbide, because gallium nitride has almost similar properties, as we see in silicon carbide. So we talk about silicon carbide, and also the market for silicon carbide is much bigger compared to gallium nitride. And reason being, the manufacturing process of silicon carbide is much more stable and low cost compared to gallium nitride. And that is why you see a lot of companies using silicon carbide for their various power applications. So silicon carbide is basically a molecule of silicon and carbon with a strong covalent bond. and basically they are arranged in the lattice structure, they are arranged in a hexagonal structure, and because of that thing it offers a very wide band gap semiconductor properties. So typically it is in range of 3.1 electron volts, 3.3 electron volts is the energy band gap for silicon carbide. And as the band gap is also high, that is 3.3, it also has a very, it can withstand a high electric field, which means that even if you apply a high voltage across it, it does not break down. There is no breakdown and there is no free carriers that are released for conduction. And the chemical properties of silicon carbide is, it provides much better thermal conductivity and thermal stability than silicon, which makes it very ideal for, in applications where reliability is very, very important, because these work at a very high temperature and they also work at a very high voltage. So for such application, it becomes very, very ideal. And it is very important to have a high thermal conductivity because, when the temperature of a semiconductor rises, it is important that that heat is also kind of drained out on the heat sink or through whatever medium it is. If it does not happen that way, then the junction temperature increases and it leads to malfunction of the power device. So the advantages of silicon carbide and gallium nitride over silicon, there are many. I told you about the high thermal conductivity, a very, very important property for high reliable systems. So typically for rail traction, for space applications and all, they prefer a high thermal conductivity, low thermal expansion, low power and switching losses because they have a very low RDS on. Silicon carbide based MOSFETs have low RDS on and also has a high electron carrier mobility, which reduces the switching losses also. They are highly efficient, energy efficient because there is less power loss. It can operate at a high operating frequency and temperature that we already discussed. Because of the high band gap, we can design the same MOSFET for the same breakdown voltage in a smaller die size. So that also reduces the space that it takes. Then obviously it has intrinsic body diode, it has excellent thermal management and reduces cooling requirement, and has a long lifetime. So if I have to summarize, basically higher operating voltage, it can go up to several thousands of voltage. Second is temperatures. It can work at a elevated temperature of like more than 250 degrees centigrade, and greater power efficiency and higher switching speed. So typically for higher switching speed, gallium nitride is used because it has the mobility much higher than the silicon carbide, and that is why for RF applications and for high frequency applications, gallium nitride is the preferred device. Okay, so I have already discussed this thing, like, okay, the silicon carbide has 3 times greater band gap compared to silicon, and that is a special property which leads to your high voltage, high temperature operations, high frequency operations as well. Here we talk about the ability to withstand high voltages. That I will discuss in the next slide because there are some numbers out there. So if you see here, so this is a good comparison between silicon carbide and gallium nitride. And if you see on the 3 fronts, that is high temperature applications, high voltage applications, and high frequency switching. So for the high switching applications, you see the gallium nitride is better than your silicon carbide. But for rest of them, I think be it high temperature application or high voltage application, this works out to be the silicon carbide is better. And you see the silicon is the inside circle, which means for these particular properties, both silicon carbide and gallium nitride functions better than regular silicon. And if you see here the material properties, a comparison between silicon and silicon carbide, band gap is 3 times. The critical field that it can withstand is also 10x. This is 0.3 and this is 3. Electron mobility for silicon carbide, it is smaller than silicon, but for gallium nitride it is much higher. It is in range of 2000. So for high frequency applications, that is where the gallium nitride is used. Again, electron saturation velocity, it is twice as good as silicon. And thermal conductivity is 3 times better. This is 1.5 watts per square centimeter Kelvin, and this is 5. Okay. So in most of the parameters, your silicon carbide is better than silicon. So this is the application areas of the wide band gap devices, that is silicon carbide and gallium nitride. So as you can see, for low voltage application and for low wattage applications, it is typically silicon that is used. Beyond that thing, we use gallium nitride. Again, this is till 1 kilowatt power rating, and for voltages which is somewhere close to say about 600 or to 700, gallium nitride is using. So most of the fast chargers that you use for your mobile phones or laptops, they are most probably built on the gallium nitride based power devices. Okay. And then comes, for high voltage application, that is where your gallium nitride and silicon carbide both are into picture. So if you see here, data centers, your residential solar applications, your cars, electric cars, and for all the applications that requires a high wattage, power wattage and high voltage, are typically silicon carbide is used. And in terms of market market size also, silicon carbide is also much bigger than your gallium nitride and silicon, at least for the power applications. So this gives the total available market and the compounded annual growth of both gallium nitride and silicon carbide. So as you can see, the market size of silicon carbide and gallium nitride is close to like 13 and $15 billion in like 2026, and it is growing at a much bigger rate, that is 8%, and silicon carbide is growing at 12%. So this is a good opportunity for India to tap into this market. The reason being, it can, the technology is not very, very advanced, which means that we can set up a fab at a much lower cost, okay, for this compound semiconductor. And recently, there is a, company that we used to use these devices much early on in like early 90s and all, that is RIR. So they have set up a fab for the silicon carbide, and the forecasted market for the silicon carbide and gallium nitride in 2029 is $8.7 billion. And this is growing at a compound rate of 35.5%. So there is a huge opportunity for India to invest in these technologies because there is a huge growth rate year over year, and there is also a large market size as well. So as you can see, the demand for these devices for various applications. So the electric vehicle has increased, sharply in the last few years. After that thing, your solar photovoltaic cells, and then comes your rail transport, and then the other things follow. These are major players in silicon and gallium nitride device marketplace. So this is one of the pioneers in the silicon carbide, Wolfspeed, and this is again a Japanese company. Mitsubishi is Japanese, Infineon is again a French company, Toshiba is Japanese. RIR is an Indian company, and they have recently got into manufacturing of silicon carbide. Same thing with the CDIL also. They are also into getting into silicon carbide manufacturing. Again, this is also a very established and old company in India. And the new one is the Agnit. They are getting into the gallium nitride manufacturing. In fact, it's a startup from IISc. They are already come up with the gallium nitride wafers. So that's all, folks. Thank you for your time. So there are technologies, but until they are manufactured, they are able to be manufactured at a low cost, it doesn't become a mainstream. But there is a, there is a aluminum nitride research is going on, and then there are many other semiconductors on which, and basic thing what they're trying to do is somehow if they can improve the electron mobility, because that's a primary factor that impacts the high frequency application. So they are trying to work out different ways to increase the electron mobility of these compound semiconductors to get a better higher frequency.